Before we go very much further, we need to revisit the idea behind a reciprocal and an inverse because sometimes they can get confused. When we talk about a reciprocal, we are actually talking about the multiplicative inverse of something. So for example, skip down here to 3 times 1/3. We know that 3 and 1/3 are reciprocals of each other. We've used that terminology. You should be very familiar with that terminology. And we know that when we multiply these two numbers together, we get back 1. Just like if I were to represent x and its reciprocal, if I multiply those two numbers together, I get back 1. And if I put this in terms of trig, we know cosecant and its reciprocal sine are reciprocals of each other. Again, if we multiply them, we get back 1. In other words, they are a reciprocal and the multiplicative inverse of each other are, that's what they are. A reciprocal is the multiplicative inverse. Now that's different from the inverse of a function. Okay, so a function inverse is represented as f inverse of x. In other words, algebraically, if we were to find an inverse, we would switch the x's and the y's. If we looked at the graph of a function and its inverse, you would see that the x and the y coordinates would be switched. The easiest thing for us to use for an example would be maybe logs and exponents. Logs and exponents are inverses of each other. So another one would be to look at maybe a linear equation. If I had the equation y is equal to 3x plus 2, and I wanted to write the inverse of 3x plus 2, I would switch the x's and the y's. Okay, solve that equation, which I did here on this left-hand side, and I got it down to this. So in other words, y equals 3x plus 2 and y equals 1/3 x minus 2/3 are inverses of each other. So I just want it to be clear to you, I suppose, that you understand that when I'm talking about the reciprocal, we would talk about the multiplicative inverse, okay, because the reciprocal, a number multiplied by its reciprocal gives us 1. That's not necessarily the case when we're talking about functions. Okay, so I just want you to be clear on that, because as we move down into this section, and this section is really about finding the angle measure, okay, finding the value of theta, in other words, if we know what the number is. So this time, going back to our idea that if I want to know what is the cosine of some angle that gives me, that when I take the cosine of that angle, I get back 1/2. Okay, so the cosine of what equals 1/2? That's the scenario that we're looking at in this particular video. Hopefully you remember that the cosine of 60 gives me 1/2. And so that's kind of what we're doing. Now the example that we're going to look at right here says I want to find out what the value is if I want to find out what theta is if I know that the value is given. And we're only looking at theta in the first quadrant. Okay, so we're only looking at angle measurements that are between 0 and 90 degrees. So the way that we do this is pretty straightforward if we're given one of our sine, cosine, tangent functions. And pulling up our calculator, notice that I have sine, cosine, and tangent, and right above, I don't think you can see it on my calculator, but you have it on yours, right above sine, cosine, and tangent would be sine inverse, cosine inverse, tan inverse. And that's what we're going to use if we're going to return an angle measurement. So we would do secant cosine, and I'm going to put in this value right here, which is 0.921185541. And what does it return? The degree measurement. Okay, so if I take the cosine of 22.8 degrees, I get back 0.921. Okay, Okay, so that is an actual degree measurement. Now, how many of those decimals are we going to be using? Well, to answer that, in order to be able to give the correct answer back, say, on a computer or whatever, we want to talk about the digits here. If I were to count up the number of digits that are given in the problem, I have 1, 2, 3, 4, 5, 6, 7, 8 digits being displayed right here, not including that 0. That doesn't count to the left of the decimal point. So I have 8 digits. So my solution must contain 8 digits. So I would choose 1, 2, 3, 4, 5, 6, 7, 8 for my answer. So in other words, the 3, 5 over here would not show up in my answer, and my answer would be 22.899999. I think I got all that, but that's what it is. Okay, so that's how we know how many decimals to give back, unless we're told otherwise. Let's practice this again for cotangent. Remember, I don't have cotangent up here, so I can't use an inverse cotangent. So instead, we're going to go back to the idea that we know what the reciprocal of cotangent is, and that's tangent. Now this looks like, we're going to think of it in this way. We can take the inverse tangent of something on my calculator, but how do I represent the reciprocal portion? That comes in as 1 over, and then we put this value down here in the denominator. Okay, so we use the reciprocal value or the reciprocal concept as well as the inverse concept to get an answer for this. So this is going to be second inverse tangent 1 divided by 1.4466474. Okay, and in other words, if I were going to take the cotangent of 34.65 degrees, I would get back 1.44. Again, how many numbers do I use for the answer? That comes from the problem. If I have 1, 2, 3, 4, 5, 6, 7, 8 digits in my original problem, then my solution must contain 8 digits as well.